first presenter today is Brian Thomas. He is the Geocomp Territory Manager for the U.S. South region. Brian, would you like to say hello and introduce yourself?
Yes, good afternoon, good evening, good morning, depending on where you're tuning in from. Just like to welcome you to our webinar here. A little bit about myself. I was born and raised in Ohio, just on the banks of Lake Erie. Attended Kent State University, majoring in political science and minoring in aviation. I've been with Geocomp just about a year now, and prior to that, spent many years in the material testing industry as well.
Awesome. Thanks, Brian. Our second presenter, also a Brian Jones, who's the Global Product Sales Manager for Geocomp. Brian, care to introduce yourself?
Yeah, thank you, Jay. And also, as Brian said, thank you to everybody for joining us here today. Hope this is going to be an informative webinar for you, and we really appreciate you taking the time. So I joined Geocomp in 2018 with an extensive background in geological and geophysical consulting, with about 11 years experience in high-tech equipment for engineering applications. In my role here as the product sales manager, I'm responsible for leading and executing strategic growth of our product group sales. Here we're talking, about the fully automated geotechnical testing systems, but Geocomp has other field instrumentation and pavement sensors as well. I manage our domestic sales team and work with our network of international distributors and also work to help support the needs of our clients. I've got a Bachelor's of Science in Environmental Geoscience from Boston College, and I actually live here in the Acton, Massachusetts area near the Geocomp headquarters. Okay, so let's kind of move into our presentation here. So here's our requisite outline, and you guys can kind of see what we're going to run through. Basically, kind of take it from the beginning, why we're testing, and kind of run through differences in equipment, those benefits and the potential solutions we have for different types of labs. You'll notice we have down at the bottom, you should be able to see we've got about 44 slides. We do have 44 slides, and we're hoping to take about 45 minutes here with some questions in the end. I just want to mention, most importantly, kind of as we're going through this presentation, consider some of the issues maybe, you're facing or some colleagues you have that are facing issues in their labs, and some of the solutions you may find throughout this presentation. I just want to mention, Jay put out there the PDH credits. Just want to warn you that there are going to be four questions throughout the presentation. We've tried to keep them simple and lighthearted. So before we get going here, we're going to poll the audience and kind of give you a sense of how this question and answer is going to work, multiple choice. So we're going to poll the audience and see generally what level of experience you've had with automated systems. So hopefully you should have a pop-up on your screen, and that's, what level of experience with automated testing systems do you have? Three choices. You're currently using them, and you're here to just maybe learn a little bit more. You've used them in the past, maybe in university or academia, or maybe little to none, and you're here to learn a lot about the differences in the equipment. So if you could put an answer in there and click submit. If it didn't pop up on your screen, you may find that the questions are in your side chat. So we'll let that roll here a little bit, kind of see where we stand. Looks like we've got a fair bit of people, about 56% who currently use systems, 31% little to none. So we've got a pretty good spread here. And that's good. So, we're going to cover the range of topics. All right, so starting from the beginning, why do we care about soil mechanics? All right, and I just want to put out there, we're really only going to hit on the high level aspects throughout this presentation of geotechnical engineering, lab testing requirements in this webinar. We're not going to dive too much into theory of geotechnical engineering. I'm sure a lot of you are already experts in that. So, any more detailed questions, things like test settings, soil mechanics, please save those. We're happy to answer them after the webinar and answer anything we can. So, looking at this structure, everybody should be pretty familiar with this. It's the Leaning Tower of Pisa. And whether you've taken soil mechanics or not, you've seen this. And basically, this is why you don't want things like this to happen to your structures. Whether it's a physical building, an embankment, whatever it may be, you don't want these sort of things to happen. And so this structure was built before kind of the fundamentals and lab testing were brought on. 600 years later, when Carl Terzaghi kind of gave birth to the modern soil mechanics and giving us the ability to better predict soil behavior and then better be able to design structures and safer structures using lab testing so issues like this don't happen. So why are we testing geomaterial in general? And I just want to note here, I mean, we put out geomaterial because there's testing going on a range of materials, right? Soil, rock, geosynthetics. But in the name of time here, we're really going to focus on soils today. So why are we testing soils? So I'll put your attention down here to this quote from Carl Terzaghi. That soils are made by nature, not by man, and the products of nature are always complex, and that's really the essence of it. Soils are different. They're different differences in grain size, the ability to drain water, compressibility, shear strength, load-bearing capacity. These are all things that affect what can be built on top of the soils. All right, so we'll talk in a little more detail about the testing used to determine these properties, which are also dependent on the type or location of what's going to be built. Is it a large building in a coastal city with soft soils? Is it an embankment on the side of a highway, a bridge? There's all kinds of infrastructure to consider and engineering design requirements for each, which we're not going to cover in this webinar, but it's crucial to know that this inherent variability and the unknowns are the reasons why we absolutely should be performing lab tests. All right, so I'm going to run through just a few common examples here that you may be familiar with and what types of tests and what we deal with through some of these. But first is our first question, right? So as I mentioned, we're going to quiz you a little throughout here. What's one difference in soils that makes lab testing important? So we just kind of ran through this here. Is it shear strength? Is it the color? Or is it the soil location? Click your answers in there. Give everybody a quick chance to vote. As I mentioned, we're trying to keep these easy and lighthearted. Everybody gets a PDH. Okay, so the right answer was shear strength, and it looks like pretty much everybody got that correct. Okay, so the types of tests. I want to talk a little bit about these, and then we'll get into the application of them. These we like to break it into about 4 general categories of testing. So there's consolidation, strength, permeability, and cyclic and dynamic testing. Consolidation testing, there's several variations. 1D incremental, constant rate, row consolidation, or hydraulic consolidation. These tests are mainly performed, for settlement analysis, and that comes into play with designing foundations, slabs, and many other types of structures. And we're trying to get a sense, how the soils are going to settle. Is it going to be differential? How do we have to design this structure to account for that? Strength, there's a range of tests to very quick, easy, often almost considered index level tests like unconfined compressive strength, CBR, direct shear. These are very quick tests, UU triaxial. And then we can take that into, a little more advanced tests, direct simple shear, triaxial, that are going to really give us these shear strength parameters. Permeability, we're looking at hydraulic conductivity, how well is the soil is going to drain. And then we get into the cyclic and dynamic tests, and these are more for cyclic strength, assessing how soil behaves when it's shaken, either by earthquake movement, wind, waves, blasting, things like that. All right. So these are kind of the general categories that we're looking at. So we'll take a look at a few examples here. First one being a deep excavation. Now this was a project in New York City, and it's kind of an example of this. And if you look in this photo, you see the struts at the top, and they're really holding back, all these pressures within this foundation so that it can be built deep into the soil safely without collapsing. Now I'm going to try and draw a little bit on this image. Hopefully you can kind of see what I'm going to put on here. But essentially, you've got some walls here on the sides, and they're digging this foundation, and we're deep, right? And so the water table is likely way up here somewhere, way up, and so you can see it's very wet down here. So there's some interesting factors that are happening that being well below the water table. You have all sorts of stresses coming in here from both sides, from all the weight and pressure of the material here. So testing needs to be done for a variety of reasons. It might be done for the temporary condition of the excavation. How many supports do we need to put in here? Maybe it's a water management plan during construction. And or possibly for the final condition when the structure is going to be built on top in the foundation. So the soil here is going to be tested probably for triaxial, direct shear, consolidation, and triaxial, and the types of triaxial you consider are mainly going to be for slope stability design throughout the excavation and construction. And I'll draw on the next slide here to give you a little better sense of that. But that's going to allow them to design and get a design scheme based on these horizontal and vertical pressures that are going to be felt by the foundation. So this is key to get lab testing and see how things are going to behave. Another application we might consider, here's an earthen dam. This is an earthen dam that holds back coal ash from a power plant, which basically is a leftover man-made material from burning coal at a power plant. And so here, we might be doing testing because we've got both natural and man-made materials, which would have entirely different properties. Is one reason why we might be doing some testing. But just kind of considering the earthen dam in general, the properties of the soil need to be known so that the slope design, the angle, will support the pressure of the water, prevent harmful seepage. So internally, we need to make sure water's not seeping through the structure, and overall to prevent collapse or catastrophic failure. So let me bring out my pen here again, and so let's look at a common slope stability diagram, which many of you are probably quite familiar with. And what we're looking at is kind of the way the failure often occurs and where and why we want to do testing. So here's our slope, and often right here we're going to be looking at triaxial tests, and these may be CU triaxial tests, and this is all going to depend on water table and where we are and what type of tests want to be done. But typically we're doing a compression test here. Triaxial CU. Down here in the horizontal slip plane here, we're doing probably direct shear, direct simple shear, depending on where we are in the water table. Direct shear typically above, simple shear typically below. So let's say we're doing some sort of horizontal shear test here, either for DS or DSS. And then out here at the toe, we would be looking at some sort of triaxial extension tests as we have some upward forces coming up there. Internally, we got to consider this, seepage and drainage effects kind of coming through this dam. So we're going to run some permeability tests. Possibly there's a clay core to this system, or maybe just for general drainage design. And then lastly, consolidation tests. So, we have a lot of weight of material that's going to be placed here for the dam, and how is that going to settle below it, and how that may affect the dam and the design. So those would be the types of tests we would look at here. This is an application that we're seeing much more of over the last handful of years, and then that's the offshore wind turbine and the offshore wind industry. There's many forces acting on these structures. Wind, waves, battering it. And then you have to consider both above, what's happening to this structure above as well as below and down into the foundation. So, we could be looking at static or dynamic forces acting on this structure. So what they're going to look at here, is probably the pre-consolidation pressure of the soil, under the structure that needs to be found, down below the ocean. So again, if I can draw here, hopefully you can see this. We've got our ocean waves at the top, and we've got our structure. And I'll give you kind of a crude looking windmill. Sorry, with the wind turbine. And your slope, who knows what it looks like down here under the water. It could have a slope to it, just like we talked about in the last few applications. So they're going to do consolidations to kind of see what's going to happen as the structure and the load is there over time. And this could be something like constant rate of strain consolidation, get a nice stress history. We could be looking at triaxial compression tests again, either extension or compression, depending on the last image I drew for you. Consolidated drained is a good application here, triaxial, for kind of the long-term behavior of the undrained soils. And then, we're looking at the cyclic effects as well. So we're going to be doing cyclic direct simple shear, cyclic triaxial, and looking at the cyclic strength of these materials, liquefaction potential, what's going to happen as they're being battered with these dynamic forces. So, cyclic direct simple shear, cyclic triaxial, maybe even resonant column tests. And the static tests I mentioned are going to give you kind of the quick undrained shear strength parameters to really help plan these cyclic tests. So that's kind of captures kind of the whole gamut there, from the static to the dynamic tests in one general application. This is an application and kind of a set of applications here that really is quite an interesting phenomenon, and that's in earthquake engineering and liquefaction. And you may have heard of liquefaction and seen results like these in the news. And this is a process by which sediment that's saturated temporarily loses strength, and that's typically by earthquake shaking, but it could be other things, blasting or other things causing shaking of the materials. But it starts to behave like a liquid. So if you think of maybe wiggling your toes in a wet beach right near the sand, near the water's edge, and you're kind of doing that, and your feet kind of settle in, and the water and soil kind of comes up over. And that's basically what we have going on here. And liquefaction occurs, in these sandy soils. They're saturated. Water's is filling the pores and the voids between the soil particles. And then prior to an earthquake, the water pressure is relatively low and influences how tightly these soil particles are held together. And the earthquake shaking, causes the water pressure to increase. Soil particles start moving freely in the water, and to the point where the soil behaves like a thick liquid. And you end up with some of the effects you see in the images here. And, this topic of liquefaction in this overall arena of earthquake engineering, they've been hot topics for the last 10 or little more years, due to major events going on around the globe. And one of those that's been a hot button item lately is tailings dam failures. We had a major event a couple of years ago in Brazil, and they just seem to be popping up more frequently, as well as catastrophic earthquakes. One as recent as 2021 in Haiti. We also had two major earthquakes in 2011 in Tohoku, Japan, and Christchurch, New Zealand. These are major events, and they can cost thousands of lives, billions of dollars in repairs. So, it's really critical that we design proper structures in these seismically active areas. And the proper design can only be achieved by performing these cyclic and dynamic soil tests. And to achieve the really precise results we need, these advanced tests they really should only be done with automated systems. And so, it's really key that we really discuss kind of the automation. Okay, that leads us into question 2. So what is one popular soil strength test that has value for a variety of applications? And a key here being soil strength test. As I mentioned those categories earlier, is it consolidation? Is it triaxial? Or is it dirt curls? I'll give you a hint. It is not dirt curls. So we'll let everybody get their votes in. And so the correct answer here, and again, the key was the soil strength test, consolidation test. Great test. A lot of application across a broad range of uses. But the answer here, strength test, is triaxial. So triaxial would be the strength test we were looking for. All right, but before we dive into automated systems and what's going on there, I think it's important we quickly look back. Let's look at the evolution of soil testing and how it developed, since the introduction of the fundamental concepts of soil mechanics. Laboratory testing, it's provided the lifeblood of the advances in modern geotechnical engineering. And I'm not going to read this table. I mean, you can kind of look through it while I'm speaking here, but really to kind of summarize this table, it came from a 2003 State of Practice lecture by Geocomp's founder and CEO, Dr. Alan Moore. And it's really an attempt to capture the central role of lab testing from every decade of progress in the field. So, in the early years, we're simply tying lab testing to field and theoretical results. All right, then the 50s and 60s characterized by a little more widespread use of straightforward, simple equipment. And then, however, as we moved into the 70s, it got more involved, complicated, sophisticated equipment, and it required specialists to operate this equipment. We're talking devices like cyclic triaxial, constant rate of strain consolidation, and they required expensive electronics, frequent calibration, and again, you needed experts who kind of knew what they were doing to run the equipment, analyze the data, produce the reports. All right, and so these conditions led to designers really getting away from doing the lab testing. They were resorting to more conservative estimates of soil parameters based on published values, experience, maybe use of field testing. And this kind of went into the 80s. But then competitive pressures came along, and recent decades have led engineers to really seek ways to win projects by reducing costs. And this is where really the advances in technology and the role of automation came into play. All right, so in the late 90s, early 2000s, automation is still quite young. But in the testing industry, over the last 10 to 15 years, we've seen this major impact, where companies who have incorporated it into their labs have risen to the top, in terms of productivity, profitability. Well, a lot of the researchers are now able to get highly precise results on a reliable basis for their publications, and this is all huge stuff for laboratories. All right, so now I'm going to kick it over to Brian Thomas, who's got a great bit of experience working with both manual and automated testing systems. Brian?
Yes. Well, thanks, Brian, for getting a little more in depth on why we need to perform the various geotechnical tests, and for that brief history lesson. So in comparing manual to automated, here's a look. If you look on the left, this is common equipment for 1D incremental consolidation testing, which is a foundational lab test for many projects. So geotechnical testing really started with performing these manual tests, again, like the image on the left, comprised of setting weights and then checking the displacement of soil at predetermined time intervals and comparing the changes. These tests would run over the span of many days and many nights, meaning that the lab technician would have to stay through the night in order to get the data that the test was producing. Here's a manual panel pressure comparative to a automated on the right. On the left, you're probably familiar with these. These are manual panels with air pressure supplied through pressure regulators, in which you obtain your test data by reading the volumes off the graduated burettes. This method is not very accurate. It's prone to operator subjectivity, and it's very time consuming. And if you were to miss one of your readings, we basically had to go back and guess. Many current and former lab techs remember setting alarm clocks and sleeping on cots in the lab. And that was the dark ages, of course, before the adaptation of automated testing. And to come full circle, this is really one of the reasons why automated testing was invented to begin with. We can now improve the quality of testing while lessening the strain on our staff. With a fully automated system, there's no more sleeping on cots, no more all-night shifts. And now we'll switch to the reporting aspect. On the left, you'll see an example of a manual test run with manually recorded results. You'll see potential for human error here. Luckily, in this case, the observer's writing was legible, but what if it wasn't? What if a number 8 looked like a number 3 or vice versa? Or the observer made an error with the graph or plotting the data points. The image in the middle and on the right, those are examples of automated test results, clean, crisp, and precise data. We'll shift to the benefits of automation here. So some of these benefits include, as you see there on the left, automated geotechnical testing has made running tests and collecting data easier while being far more reliable. Most tests run from beginning to end with little to no interaction from the user, which frees them up for additional tasks in the lab. Automated systems eliminate human errors. There's no mistakes in writing numbers down or doing calculations. Automated tests, they also offer increased and evenly distributed data points, creating consistent high quality results and far greater data volume available to assess. An example of time savings, say we're testing silty clay that's using the old manual method. Typically that would take 16 to 18 days to complete. In contrast, a fully automated consolidation system will only take about a day or two to do the same exact test. Looking at the man hours that would take on the manual system, you're talking between logging and loading constantly, anywhere between 8 and 16 hours. With an automated system, you're going to cut that labor time down to just an hour. This reduction in labor allows you to perform additional tests and do, like I mentioned before, other tasks around the lab, increasing your productivity. Back to this image again. The consolidation systems. One automated system, as you see pictured on the right, can perform and replace up to 10 of the manual systems, as you see on the left. So instead of placing the weight on the mechanical arm and waiting the full 24 hours, the automated system will place the load, 90% of that load, within 1 second, and it monitors the sample, compressing it until it has reached primary consolidation. The end of the primary consolidation is when the excess pore water pressure has completely dissipated, which means the pore water has been pushed out of the sample and the weight is resting just on the grains of soil. At that point, the test automatically will advance to the next load, also called the next phase of stress, without having to wait the full 24 hours required by a manual setup. Brian will go over in a couple slides with you a little more in depth about the time and labor savings. Looking again at the manual pressure panels versus the automated. I mentioned before, there's errors in reading. There can be errors in reading the burettes. There can be errors in opening or closing the wrong valves and mixing up the test data. You'll see the sheets of paper there on each of the tests, and so on. Automated flow pumps, like the ones you see in the image on the right, precisely controls pressure and volume in a test cell. They can resolve volume changes as small as 0.001 cc and maintain a pressure to within 0.05 psi up to a max pressure of 500 psi. The only external inputs into the automated system on the right is water and power, which that means no more noisy and unreliable air compressors. Brian?
Okay, so let's as Brian mentioned, let's take a look at these numbers and time and labor savings a little deeper. And this is pretty busy here, so I want you to really kind of focus on these two columns. We've kind of talked, why the automated systems are better than manual, but this really puts the numbers on it. So if you look at these columns, and this is for three of the most common types of tests, consolidation, triaxial, direct shear. All right, these percentages are amazingly high. I mean, you compare them to the old way of doing things. I mean, we're looking at 50 to 97% time savings, and kind of pretty much the same in labor savings. All right, so these are huge, phenomenal numbers and differences you could have as an impact in your lab. Now, so this is a pretty busy slide, I know. So let's kind of tear it down and look at just consolidation. So we take it here, and again, let's look at these two columns. As Brian mentioned earlier, a single automated consolidation system can replace upwards of 10, typically anywhere from 5 to 10 manual odometers. And that's really reflected in the numbers here. And as Brian mentioned, you 16 to 18 days or so for testing, depending on the type of soils. It's pretty much the same manual. You're doing those loads every 24 hours. But with the automated, doing primary consolidation, we're looking at anywhere from a half day to a maximum of 3 days. I mean, this is phenomenal time savings. And so, you can really take advantage and use that space properly in your lab. And I want to bring out one of the most dangerous phrases in the language is we've always done it that way. The data really shows the impact automation can have. So why do you want to keep doing it the old way just because the manual systems have been here, I've you've used them for historically, and you can also think of this as you can use these savings to test more samples. So in a shortened period of time, it could allow you to better capture spatial variability in the underground, remove some risk from your projects. There's all sorts of ways you can think about how you can employ the time and labor savings here. But in the end, it's obvious that automated users they're getting faster, higher quality results. They can deliver to clients more quickly. They can publish sooner, and these things you can really use to your advantage. Maybe that's taking the lead against your competition. You're able to produce results more quickly to local clients, or maybe on the university side, it allows students, researchers, professors to advance their learning or their careers at a faster pace. Now these are big things to consider. So let's kind of take it maybe a little more to the commercial side and look at the financial aspects of this. Manual versus automated potential in terms of earnings. And this is some of the more common tests. And having the ability to run tests faster, it allows you to complete more annually. In most cases, it's 2, 3, over 9 times the tests of numbers of tests you can get into. And I want to focus attention here on these two really common tests. CBR, incremental consolidation. And let's really take incremental consolidation because we've been talking a lot about that. We can see, you can do about 9 times the number of tests annually. And you look at what that means in dollars. I mean, all of a sudden we're going from $8,000 to making $75,000 in the same amount of time. All right, so this is, in terms of financial gain, there's a lot here as well. All right. Now let's shift it over from the common to, as Brian mentioned before, these automated systems are going to allow you to more easily bring on advanced tests in your lab. And, although triaxial may not be a real advanced test, we have some of these other ones, cyclic testing, resilient modulus, simple shear, cyclic and dynamic testing. All right, so these all come into play when you get into automation. You can see, in the manual columns here, not even applicable. You can't even run these tests with manual systems. Sure, maybe in the research realm, universities, you can put together some systems and run them somewhat manually and digitally and get some data, but you're not doing that in kind of a production sense. So let's key in on one of these again here, and I'll bring the attention to resilient modulus, because I mean you can look at the numbers here. I mean you can run 1,000 resilient modulus tests in a year, and that could be upwards of $400,000 in revenue for financial gain for a potential lab here. And I bring this one up, the resilient modulus, in kind of comparison to the last slide, the CBR, and those two tests have been used for roadway and transportation engineering designs, but RM really has come more into play in recent years. And historically, although it's been around, it's been avoided mainly at the DOT level for many years, because it was just too complex of a test. The equipment was too complex. Getting the data was too complex. They weren't confident in the results. But now with the ease of automation, computer control, it eliminates all that complexity and can greatly boost the confidence. So we've seen DOTs really start latching on to the using the resilient modulus for designs, project requirements, even all the way up to the Federal Highway Administration level. And so it's you really should kind of think, if you're a commercial lab, what's going on in your state. I mean, we're seeing a lot of states really moving to resilient modulus testing as the core test. And so this might be the time to bring this type of testing to your lab and consider automation. What's happening? You might want to be the first to capture the market in your region with this type of testing. I mean, certainly you don't want to be the last. All right, so there's definitely a lot of financial gain to consider here in terms of automation. Okay, so that brings us to our third question. All right, and I like to kind of put this out there in terms of kind of the three P's of automation. And automation has benefits for, as Brian and I have talked about, productivity, precision, profitability. So which of these is a key benefit? Is it nearly eliminating the human error aspect, logging data manually, entering data into a computer afterwards, faster, consistent, reliable results? Staff can handle more tasks while the computer is doing all the work, or is it all the above? So you might have noticed we were a little tricky with this one. It's all of the above. It's all of the above. So this is really what it brings to your lab. All right. Okay, so now I want to give you a visual perspective. All right, I'm going to get this video going. And I'm going to run it through once and talk here, and then I'm going to run it again. So this is a fully automated lab at Geotesting Express. There's almost 200 automated testing units in operation in this lab. Okay, now I'm going to run this through again, and I want you to look in this video and see how many people are logging data, trying to control these systems. One, oh, there's two. What do we got? Maybe maybe third. So two to three people. There's 200 units running in here. I mean, there's pretty much nobody in here, and these machines are running. They're collecting data. 75% of these systems in this lab at any given time are actively running tests without need to, constantly being monitored. Changing valves, changing loads, logging the data. I mean, they're doing it all for them. This is kind of the scale that you can get to, and you can add these systems and not have to bring on additional staff, which is another key aspect. Right. Okay. So these are the type of tests you might want to consider automating, and we've talked a lot about the consolidation, the strength test, but this is a list, and so a lot of your labs, you folks may be running a lot of these tests right now, and maybe you're doing the consolidations, the shears, the CBRs, and you're really wondering how to take your lab to the next level. It's automation. it's automation. So, bring in now you can do triaxial tests much more easily. Start bringing in these cyclic and dynamic tests like the resilient modulus I mentioned. That's becoming more popular, or is really popular right now. Much easier permeability tests for your fine-grained soils that automation can really help push and get you a proper flow for that level of permeability testing. All right, but let me kind of tear this down a little for you and kind of give you a sense of the other aspects of automation. And this is generally the case for most automated systems, but maybe not all. But in terms of the unit you see here on the left, an automated direct shear, the nice part is it's not just a direct shear. So you have manual units, the weights like Brian showed earlier with the consolidation units. They are what they are. You're getting consolidation. You're getting a direct shear result, and that's really it. But when you take it into the automated world and have these types of systems, you can be performing multiple tests on a single unit. So a unit like this, that you might have purchased for direct shear, you can keep it busy running all of these other tests. The really common 1D incremental consolidation. Maybe you want to use it. You get a project that requires a direct simple shear. But in the end, this investment, it may be a higher initial investment, but this equipment you can keep busy running any type of test, any time of day. So it's really such a versatile unit as you get into automation. You take it up to the triaxial level now, not just a triaxial. So you got a load frame and a couple automated pumps like Brian talked about earlier. You can run all of these tests with a single unit. This is one machine. So, you think about the scalability in your lab, scalability of tests, the space savings, and being able to put other tests in your lab. All of these can be run on one unit right here. All right. So, I hope that really puts it in perspective, what you can do with automated units. So these are some of the core features, I'll bring up, and I'm not going to spend too much time on this, but these are some things that are really nice about automated systems. You have the computer controlled aspect as well as being able to control it, manually on the system. So, that could be initial test setup or whatever you want to do there. But, if you're in a teaching lab and you really still have this appreciation for the manual style, you want your students to really try and do it that way, log the data by hand, it's an important learning process. You can still do that with these automated systems. You're not losing out on those aspects of the manual test and control and being able to do that. So, that's nice to know you can still do. Integrated control and data acquisition boards. You can get the analog channels, which is going to be your load cells, your LVDTs, but you can also step it up to digital channels like linear optical encoders, where if you're getting into the research realm and you want really precise measurements, you can start using these, with automated systems. Again, not every type of automated system is going to have these, but many do, and that's the high precision electromechanical setups. And Brian will talk a little bit and hear a couple slides of why that's so great. We've got safety mechanisms, on units that are going to prevent damage, over travel, safety protections on your sensors, network connectivity, remote monitoring, and Brian will comment a little bit more on that remote monitoring. But you've got, everything's connected in through the network, so you can kind of take advantage of, connecting remotely. And then being able to easily calibrate your units, right through software. You don't have to bring in a third-party contractor who really only knows how to do things with their equipment. You can start doing a lot of this yourself. All right, I'll pass it back over to Brian here, and he's going to dive into why might automation be right for you in your lab.
Hello again. So yes, exactly. Why should you consider either upgrading or adding to your automated lab? Well, we'll start off. Using an automated testing system allows you for quick and repeatable test setup. Technicians can watch the test in real time and make changes as necessary. You can remotely operate and monitor the test, and you can even take the electronic results and email them off as well. It allows you to modernize with digital management system. It means no more paper documents, no more losing that report, no more misplacing it. An automated system can perform advanced tests, as Brian mentioned earlier, such as the stress path and cyclic testing, which can't be done really on a manual system. And automation allows the testing of more samples in the same amount of time, so you can capture more tests at a given job site. Say you're given a deadline, and you only have a couple of manual tests there. Remember that silty clay and silty sand, 16 to 18 days to get a result back. So you set those in there. If you've only got 2 or 3 tests available, you're only going to be able to perform 2 or 3 tests. With an automated system, you're going to be able to get across your site at a greater capacity of tests in. You're going to cut them down to about a day each. And in that same couple-week period, you can get upwards of 14 tests done, whereas you could get only 2 or 3 if you had 2 or 3 manual systems sitting around. So you're further going to reduce risk on your project by getting more tests in when you're limited by time. Automated electromechanical test systems have additional benefits. They require little to no maintenance during their lifetime. They're environmentally friendly. They're self-contained. They're compact. It gives you an improved image to your clientele. So if you're a commercial lab, for example, that's going to equate to return business and referral business. And it's going to allow you to retain your staff with more interesting work on the modern equipment. For commercial labs, systems are operational 24/7. They are programmed to automatically move to the next phase, meaning results will get out faster, all while needing less interaction from the staff to make any kind of adjustments or advance the stages as you would on a manual. These machines will run when the lab is not staffed, such as weekends and holidays, and they don't call out sick and they don't take vacations either. For many tests, a single automated system can replace up to 10 manual units, so you maximize the use of your lab space while offering more test types for your clients with speedier results as well. The software produces complete reports with plots and tabular data. That data can be immediately reviewed, and with just a quick click of a button, you'll get a clean and professional report to send to your client. The programming significantly reduces the need for manual data entry. And again, it speeds up that reporting process time. For agency labs, it'll increase the quality control, which is vital to most state and federal agency labs. Most of these agency labs have limited or variable annual budgets, and it makes it tough to staff these labs. With less staff and less budget, it's crucial that the equipment will continue to perform for many years down the road and avoid project delays. Automated equipment will allow a smaller lab to support a variety of ongoing projects. In university labs, it allows students and researchers to benefit with real-world experience utilizing high-tech equipment. It creates a modernized teaching platform. It helps in attracting top students and top professors. It allows enhanced research with increased precision, repeatability, and more data to analyze. It permits more time to spend on evaluating the data rather than just performing the test itself. It provides remote learning option because you can log in from anywhere. And today, with the environment as it is, you may be in-person instruction one week and be called to do virtual instruction the next. And with that, having the opportunity to remote in, it allows a seamless integration as we're required to bend and to adjust accordingly to the environment around us. And then lastly, we really love to partner with universities to customize test systems, help them perform cutting edge research and advance our geotechnical knowledge as an industry. So we move on to the last question, question 4. It should populate here. Question is, what is one aspect of high quality automated testing systems that would benefit any type of lab? First choice, increased efficiency and accuracy. Second choice, you never have to clean them. Or the third choice, the computer will be a new friend for you. I'll give you a few minutes to put in your answers there. All right. And overwhelmingly, increased efficiency and accuracy is the correct answer. Now we'll go back to Brian Jones, who will share a few case studies with you.
Okay, thank you, Brian. All right, so just a quick look at, I know we're getting short on time here, so I'm going to go through these pretty quick, but just to kind of give you a general sense on some folks who have benefited from automation. This is a client, soil engineering testing, commercial lab based in Minnesota. They've got a wealth of experience on their staff, and you can see, all the automated systems there in their lab in not really too large of a space. And bringing in automation has really helped them, perform these more advanced tests like we've talked about throughout the webinar. And now they're doing, these more advanced applications for mining, wind, solar industries across the country. And their customers have come to know them, for providing, quality geotechnical tests in a timely manner, which this day and age, I mean, everybody wants things now. So, this aspect of being able to deliver very quickly is key in the commercial lab space. Okay, this is a DOT, an agency lab, like Brian mentioned, and this is Minnesota DOT. They've got, as you can see in these images, over 30 units, providing quick, efficient, reliable testing. And kind of really the key here, and as Brian mentioned, these agencies, they get limited budget year on year, and it's variable, and they don't have a lot of staff to put in these labs. And what they've seen is, the benefit of the reliability of the units they have in their lab. Some of these units have been in use for 20 years or so. So, they've made the investments in automation, and that's helped them, keep these systems going for many, many years. And they staff this, just like the image I showed you before the video, 1 to 2 people staff this lab at any given time running these units. I mean, it's phenomenal. And it really helps on the agency level to reduce the variability in the test results. And as they're doing these quality control tests, versus the manual style, which would just be, time consuming and problematic. And lastly, here we look at a university. This is an international university, University of Cape Town in South Africa. And this is a unique case where, they brought in some equipment for the teaching side, some consolidation units, direct shear, and they use that in the teaching space. But then they brought in some more advanced units, like a large shear box unit, cyclic triaxial, automated permeability tests. And what let this university do is start to bring revenue into the department. So, they have this equipment for teaching. The students use it for research, more, advanced research with these sophisticated systems. But they're also able to bring in, because a lot of the commercial labs in their area do not offer this level of testing. So now they can bring that in to their department. They're getting revenue, helps them pay for, any number of aspects in the department. So it's been phenomenal for them. Okay, so we're reaching the end here. So I'll just try and summarize quickly. I hope you've kind of enjoyed the webinar and have kind of taken in kind of really these 4 kind of core benefits of automation. So, automating the lab and in your testing is going to allow, for many advantages. All right. So not previously possible with manual. And one of these is reducing risk on your geotechnical projects, right? These systems nearly eliminate the human error aspect, going to produce test results, rapidly. They're going to be repeatable, high quality. So you can really have confidence in all your results and your designs and reduce a lot of that risk. Faster, more accurate test results. That's going to lead to better geotechnical designs, happier customers, more referrals, which is great for business on the business side, but also helps enhance research. Automated systems are going to improve the general lab experience, like Brian talked about. Right now, major topic is, labor shortages and turnover, and the ability to hire quality people. So, if they've got a good lab experience, they're going to want to stick around. They see that you're investing in the lab, and you don't have to train people as often. So, that's really key. And the appearance itself of your lab, as you have, clients coming in or professors, prospective students, this is all key. And lastly, enhancing research. We don't want to, focus this all on the commercial side and think it's all profitability and all that. There's really a good aspect here on the university and academic side, enhancing the research, enhancing the teaching, more data, less time spent, fidgeting with equipment. And research sites can allow for faster publication, potentially leading to, quicker tenure. So that's really important on the academic side. So, that's kind of the synopsis. I really hope you enjoyed the webinar today. We appreciate you coming out. If you have any questions, Jay, I guess you'll kind of open it up here and let's see if we can get it in a few minutes.
Yeah, so definitely want to thank both of our presenters today, Brian Thomas and Brian Jones. So let's give a virtual round of applause to them for their job today, explaining the automated lab systems and the benefits that they bring. So now on to questions. So if you have a question, you can either put it in the chat or you can use the raised hand feature. That is at the top of the screen, and there's a little raised hand option. So if you do that, I will do my best to get all these questions in. We did have one question in the chat that I thought was pretty interesting. So someone had mentioned that they were cautious to use automated systems, mostly due to the maintenance. So I guess the question is, how easy are these automated systems to maintain, and do you provide any sort of trainings for people who are going to get into an automated system?
You want to take that one, Brian, or me?
Yeah, I can take it. So, I'm looking at the question here and rereading it. So again, they're electromechanical systems. So there's virtually no maintenance. Like we mentioned, there's no air compressor, there's no air valves, there's no air supplied whatsoever. So that's a lot of times people in the past have had problems with automated systems. It's really been from that source, that air source and that compressor source breaking down. As long as you keep, the only maintenance really is calibration. That's not really maintenance, but the only thing that you'll have upkeep on this, is that yearly calibration.
Awesome. So there's a question I had from my perspective here while reviewing this was so in general, what do these automated systems cost compared to a manual system? That may be something people are concerned about.
Yeah, I can take that one. Yeah, I think, we're talking about a range of things here. I mean, certainly, even on the manual side, there's a range of products, and those may be in the price range of, let's say, two to $3,000, $4,000, depending on what type of unit we're talking about here. And they could be higher than that if we're talking a different type of test. But let's take something like a consolidation unit. You could be looking at $2,000 to $3,000 for a dead weight loaded odometer, like Brian showed earlier. Whereas an automated system, depending on vendor type, accessories, you could be looking at anywhere from, let's say, $8,000 to $12,000, something in that range. So you're looking at a cost difference of maybe 5 times. But as Brian mentioned before, it basically replaces 5 units. So, I mean, in your cost perspective is generally the same in terms of investment and what that means in productivity. And then you get all the other added benefits, from automation, that then being able to more quickly and a cost-effective fashion add additional tests to that single unit. You get the space savings, you can do more tests within your general space. So, they're going to be a more significant investment to begin with, but when you consider all the factors, it's really a great value in the end.
We got a few more questions coming in here. So someone asked, which systems do you manufacture and sell? That may be more of a thing that if you wanted to head to geocomp.com to see the products that we provide. But this presentation today has been more to show the benefits of automated lab systems from any provider, not just Geocomp. And then so we've kind of hit 2 o'clock here. So I did want to just say thank you to anyone who did participate today. And kind of as anyone takes down any of the information for contacting Geocomp with any additional questions, I'll ask one that was sent to me anonymously. Is there a big difference between digital data logging systems and a fully automated system?
Yeah, I can take that one again, I guess. Yeah, I mean, there's really a core difference there. I mean, there's certainly labs out there that maybe had some older style manual systems, and they've added some digital sensors to it, like load cells, LVDTs, and that's connected to a data logging box, and that's nice. That can help you kind of resolve some of that handwritten aspect that Brian mentioned with the reporting and logging earlier, which is beneficial. But really, that's all it's doing for you. It's digitally logging that data, that's it. But if you have to place another load, if you have to, make an adjustment on the manual pressure panel, so there's still a lot of user intervention and a lot of labor still involved in that test. Really, there's a little bit of time savings and reduction in potential human error is the only benefit. But by going fully automated, you're going to place the sample and basically walk away. I mean, kind of the heart of the title of this was, kick back and relax. I mean, that's really basically it. I mean, you're going to put the sample in, walk away, and come back and get the data later. And so that's full automation. Digital data logging doesn't get you anywhere near there.